All right, so topic 2, we're going to go over an example. It is much more challenging than the one I used as the example in topic 1. So take a nice deep breath and let's dive in. I am going to say, as I'm getting started here, that I think one of the most common errors for students to make when doing implicit differentiation, when deriving with implicit differentiation, is feeling like the process just keeps going and they're not sure when they're at the end of the problem. And I will say that in general, you know you're at the end if you have dy dx equals a function. So that's really your end goal, is to get dy dx equals a function. Usually that function can be in terms of x and y. As I mentioned very briefly in the last video, there are ways to make it just in terms of x, but I'm not really going to address that in this video. I'll save that for some of our practice problems. So really, if you want to give yourself that end goal, I'll say one more time just to make sure everybody got it, your end goal is to have dy dx equals a function in terms of x or y. So let's use the example I have here. 2y equals x squared plus sine of y. Now, at first, you might look at this and say, oh, this is going to be a really easy one because we're going to derive y. It's not even really a chain rule here. Let me get my pen. I'll use what color should I use? We'll do pink because it's nice and bright. So 2y, we could just make that like 2 dy dx. It's sort of a chain rule, but not even really using what we know about implicit differentiation. But that's not really what makes this example tricky. It's the fact that y shows up twice in this equation. Did you notice that? Right over here, there's another y. So let's just go through. We've already kind of got the derivative of 2y is 2 dy dx. But let's just go through the problem one step at a time. We're going to try to figure out how to isolate dy dx and solve the problem, because once we've done that, we have our answer. Okay, so we've derived the left side of the equation. Now we want to derive the right side of the equation. Deriving x squared is pretty easy. We're just using a power rule function, so that's just 2x. Deriving sine of y, that's where we really see this idea of implicit differentiation, where we're implying that y is a function. Therefore, we have to use a chain rule. So the derivative of the outside function is just the derivative of sine is cosine, so it's plus cosine y. The derivative of the inside function is that we're just multiplying that by dy dx, the derivative of the inside function, times dy dx. Now again, it would be sort of tempting to just divide both sides by 2, cancel these 2, the 2 on the top and the 2 on the bottom, and we'll say dy dx equals blah, 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 blah. But you can't do that, and here's why. It's just like if we're trying to solve an equation for x, you need to get all the x's on one side, maybe like pull an x to the front, divide everything else away. You got to get that x isolated all by itself, or you haven't really solved for it. Well, it's the same idea here. In order to solve this equation for dy dx, there needs to only be one dy dx in the equation. So watch how we're going to do this. And this trick is really going to work basically every time that it'll be a different type of equation each time, but the same rule is going to work for us, which is let's get all of the dy dx's on one side of the equation. Again, just like a normal algebra problem where we're trying to solve for a variable. So we'll have 2 dy dx, and then let's subtract this over to the left side. So subtract minus cosine y times dy dx, which leaves us, we're doing that on both sides technically, so it's going to leave us with just 2x on the right. We want to solve for dy dx, so let's pull it to the front like a reverse distribution. Let's take, again, I'm going to keep alternating our colors so that we can see each step. Let's take that dy dx, and let's pull it to the front of this expression. We'll use parentheses. What we have left in this first term is just 2. What we have left in the second term is just cosine y. And then, of course, on the other side of the equation, we just have 2x. We're almost there. Remember I said we know we're done with this problem when we have an equation that says dy dx on one side equals a bunch of stuff on the right. We already are down to the part where we only have one expression of dy dx. All we need to do is take this and divide it away to the other side. And what we'll end up with as our answer, and actually, because I don't like squeezing things in, let me just rewrite this. So we have dy dx times all the stuff equals 2x. And in order to finish solving for this, we're going to take this and divide it to the other side. So that dy dx is the equivalent expression of 2x all over 2 minus cosine y. Sorry about that. So that's our answer. We found dy dx. So at its basis, implicit differentiation is an application of the chain rule. It's forcing us to think about x and y according to the type of variable that they are. X is a normal, just independent variable. Y is a dependent variable, which means it's really a function. It's not just a standalone variable. So we treat it as a function, which means we have to use the chain rule. And then how do we know that we're done with this problem? How do we make sure we don't get lost in the process? We're working towards the goal of getting dy dx on one side of the equation equals a bunch of stuff. And when we get it to that point, we know we're done. As long as there aren't there can only be one dy dx. One dy dx equals an equation of some kind. All right, that is where I will leave it. Don't want to overcomplicate the process, and we'll pick up with that during our class time.